Welcome to Brain Vision.
So here we have wire segments that carry a current in an external magnetic field, and we know that force is given by I times the cross product of L and B. So the magnitude of F will be I times L times B times sine phi, where phi is the angle between length and the magnetic field. And we know that the magnetic field is along this direction everywhere. So let's write that down in the figure we have. Okay. Yeah. So this is the direction that the magnetic field points toward. Now we know that only segments A, B, and CD will experience a magnetic force, since the other two segments carry a current parallel or anti-parallel to the magnetic field. So this segment is basically, so if the current is flowing like this, so basically this is the direction of current. So current is clockwise, and for BC, the current is parallel to magnetic field, or L is parallel to the magnetic field, and for AD they are anti-parallel. So for these two segments, force will be zero because the cross product is zero. Now the force, next thing, for these two segments, we can find the force by the right hand rule applied to the directions of the current and the magnetic field. Now the torque due to a force is equal to force times the perpendicular distance between the axis and the line of force. So here let's mark the force now. So for this segment, this is force is 0 for these two, and over here magnetic field is along this direction as you see from here. So okay, so current is clockwise. This is a mistake. I'm sorry for that. Oh, this is bad. Okay, there we go. Now, okay, this is the direction of current. This is a magnetic field. Then we apply the right hand rule to find the direction of force. And if you see, the force goes into the plane of the screen. So let's mark it by this. So this is the direction of force. So let me mark all the directions in different colors so they can be differentiated. So this is the direction of force, and this is the direction of magnetic field. And green shows the direction of the current. Okay, so similarly for this segment CD, this is the current, and this is the magnetic field. So we apply the right hand rule again, and we see that this direction is out of the plane of the screen. So let's call this FAB and here FCD. And force in these two segments, BC and AD, is basically zero. Now, so that is part A. Now for part B, we see that FAB acts at the hinge, and since we know that torque is given by the product of the force times the perpendicular distance between axis and the line of force, So that distance is basically 0 here because it acts at the hinge itself. So torque at AB is equal to 0. Similarly, for the second case, FCD, uh, FCD tends to rotate the loop about the hinge, so it does produces a torque about this axis. And so let's find this force first. So FCD will be ILB sine phi from here. Phi is 90 degree. So it will just be ILB because sine phi is 1. Now current is given. We know the length. So length is basically L is this length of the segment. So LCD is 20 cm and we convert it into meters while using. So this gives 1.20 Newton. Now, so for the third part, so torque for CD will be FCD cross product of the length, or we can say FCD times the perpendicular distance, which is 35 cm. So basically, this is the hinge, right? So how do I mark it? So this is the hinge. So force is out of the paper and the perpendicular distance of the force from the hinge is basically this distance, which is 35 cm. So we apply that and we get this value to be 0.420 Newton meter. Okay, that's it. So this is basically part B, which I forgot to write.